Ladies and gentlemen, please welcome to the stage, Jim Jeffers.
Hey! Hello, hello. Thank you, so many people. Thank you for coming. Hey, how many people were at the Academy Software Foundation event today? No? Nobody? Come on. There we go. There we go. Thanks. We are super excited, very thrilled that you've come here today. We want to tell you some stories. You're storytellers. We want to tell you some stories about where we're going in the creator space. As you know, we're calling this Create the Beginning. I joined Intel late 2008 for something called this. Anybody know this thing? Anybody heard of this? So there's a project called Larrabee. I guess it's an infamous project at Intel. We were very vocal about that we were doing it. Embry was an Intel Laboratories project related to Larrabee. And somebody forgot to tell Intel Labs that we canceled the Larrabee project, and they kept working. Okay? So they kept working on ray tracing algorithms. You, all of you, kept using our products and driving us to do better things and making it part of Intel's important portfolio of software. So you out here in the industry actually knew about Embry, were using it, were building on it, and inside Intel, they didn't know about us. We were like so this semi-stealth thing. Everybody says Intel's a hardware company. No. We are a hardware company. We're going to talk about hardware, but software is the conductor of all the elements. I'd like to introduce Max Liani from Renderman. We actually have been working with Pixar and actually Larry Gritz at Sony to advance open shading language and open environment, open source. You know that my rendering framework is all open source. And so what's Pixar's feeling about open source in the industry? And then let's talk about the shading language.
We believe that open source is a strong pillar of the visual effects and the film community. Open source allows us to learn from each other and share technology. And we've been partnering with Intel for a number of years now to take the technology where it needs to be. And one of the projects that we collaborated for the last 2 years is Open Shading Language. Open Shading Language is really visual programming for artists. Open Shading Language is the language that is able to compute the appearance of surface in space. We program little nodes that then are connected to this shading graph, this computational graph. So this is one of our characters, Bo Peep in Toy Story 4. And if we look at the way the surface is shaded for just one portion, like the skin of this character, this is the way one of those computational graphs looks like. So a lot of different operators that need to be computed to evaluate the quality and the appearance of that surface in space. And this graph is evaluated billions of times to compute an image. Every time there is a light surface interaction, we have to evaluate that stuff. It's a lot of compute. We had a vectorized shading language that is called RSL for Renderman Shading Language, but we adopted industry standards because we believe in industry standards, so now we use Open Shading Language, which was not vectorized, so it was not using the hardware at its best.
So you brought your knowledge, Intel's knowledge of the architecture together to bring back that vectorized environment.
We knew where we wanted to be, and we just needed a partner because this is complex development. What we achieve is that the individual open shading language operators are accelerated between 2x and 16x, which is quite remarkable. Some through other type of optimization of the native algorithm, we reached even further performance improvements. But that is only a portion of the renderer. There is a lot more going on in the render. There is light transport. There is evaluation of lights, tracing of rays. So here we see a side-by-side comparison. And this asset here is simple, but I intentionally made the shader more complicated than we'll normally have to mimic the complexity of production shaders.
You've been working on a research project, I guess, but a pretty practical research project called XPU.
Yeah,
where you bring together the whole platform, right?
It used to be a research project 2 years ago. Now it's like production engineering. We are architecting our next generation of the renderer. And this is learning everything that we had so far, including our collaboration and what came out of vectorizing OpenCV language, and bringing it into the next rendering architecture, which is called XPU. And the X is generic compute devices, heterogeneous compute. So we are very excited to see that Intel is active in creating a new line of discrete GPUs.
Great. So you're going to help us out, move in this new direction with new GPU, new vectorization. Thank you so much, Max. Really appreciate it.
Thank
you.
Thank you.
We are announcing today a goal to drive to 1,000x with the help of all of our industry partners. I'm going to just give you an overview of Intel Rendering Framework if you don't know what it is. That has been the stealth kind of project. A fair number of people know about it, but not everybody. So first product is called OpenSWR. It stands for Software Rasterizer. This is a software CPU-based OpenGL rasterization environment that we have upstreamed into Mesa. Osprey is our ray tracing environment, an SDK, an easy-to-integrate API. It kind of is at the level of an OpenGL program. So OpenGL programmers who are not familiar with ray tracing in particular can use it. It supports 3D geometry. It supports 3D volumes. It supports them integrated together. It can be extended. Really recommend you take a look at Osprey as something that provides an incredible capability. The other core thing about Osprey is it's scalable. And by scalable, I mean it works on multiple platforms with multiple CPUs, like multiple Xeons. But more importantly, if you gang together a set of those platforms, Osprey will take advantage of that. Embry is a ray tracing kernel library. We map Embry to our latest and greatest technology. Every generation, every step of the way, we add many, many features over time. Some of the features that Embry has are 6 kinds of curves and hair based on the information we got. Some people use line segments. Some people use Bezier curves. Some people use other capability as they go. Quads, motion blur, all the features that we've worked with you on to drive the best performance. Open Volume Kernel Library. This is a new library. It is actually not yet available, but you're seeing images out of that library already. We actually are showing Open Volume Kernel Library running a very large data set in the corner over here. 1.5 terabytes of data on a platform running at 25 frames per second. Open Image Denoise, we put this out for the first time in February, and many applications, both in-house and commercial applications, use it. It is, we believe, the highest featured open denoiser on the planet. I'd like to bring out Dave McGarvin from Maxon to talk a little bit about what's happening with Cinema 4D. One of the great additions that we worked hard with Dave and his team on is Open Image Denoise.
Yeah, so Intel's been a great partner, and they have free beer, so we're all happy about that, right? It's been a great day for us, so we're celebrating. We had some great releases, and today, one of the big things about R21 is the performance. It's absolutely spectacular. The Open Image Denoise is really, really resonating with our customers. You get the production quality rendering that you'd get in a fraction of the time because you can run the denoise on it. We implemented it as a post effect, so it works with pretty much all the renderers. It works with our physical renderer, it works with Redshift, and it works with all the other renderers in the industry. And you can really see really clearly there where you can go from something, not that usable to production quality. It is really, truly a great thing for us, so thank you very much.
Now, we partnered with you with Embry in particular. Why don't you tell us about what's happening there?
So Embry we've been using since version R19, and what I'm going to show you on the next slide is no Embry, R19 Embry, and then the Embry that we're going to be shipping in September with our new version. So on the left, you got no Embry, Embry in R19, and Embry in R21. Yeah, you're allowed to be loud. they're artists who are really creating things, that's going to change it for them, and it's spectacular.
What else is happening at Maxon?
So we've been doing a lot on performance, but today's actually about bigger than that for Maxon. We're introducing the Maxon for the whole world. Yeah. So the Maxon for the whole world implementation is about getting 3D to more people. 3D is now taking over, and all creative people want to somehow do 3D. So we're going to make Cinema 4D is the easiest to use software out there in the 3D space. It's the easiest to learn. It has all these amazing features, and we've released a ton of them today with R21. It's efficient, and what we're doing today is we're going to make it available to buy around the world with a one-stop online store with a new price of $60 a month, which should shake the industry. Everybody can now afford it, and everybody can get into it. And with the Intel optimizations, our customers are going to be really, really happy. At NAB, we announced that Redshift is joining the Maxon family, and it's the world's best GPU renderer, and it's used in all the Hollywood films that everybody loves. And we're going to be working with Intel on that as well, figuring out how to get that onto your GPUs.
Okay.
Yeah.
Looking forward to it. Thanks, Dave.
Yeah. I'm going to grab my beer. Cheers, everybody.
In the film animation industry, some vague polls of people, we're seeing roughly scenes upwards of 250 gigabytes, maybe on average, maybe similar to the Pixar Marigold Bridge scene. For a sci-viz application or a supercomputer generating code that needs to be visualized, we're in the range of 5 terabytes. And for something like cosmology, which is super memory hungry, you're basically modeling the whole universe. Amelia Drew, she's a researcher at Stephen Hawking Center for Theoretical Cosmology. Welcome, Amelia. Thanks.
So what we have here is a single cosmic string in the center of the screen oscillating. And what you're seeing in the blue and the yellow coming out of the side is one of the types of radiation that these strings emit. So you can sort of see the radiation being emitted in a dipole, which means sort of 2 lobes coming out of the side. And so the visualization really enables us to get some physical insight into what's going on with this radiation.
And I made the statement that cosmology uses a lot of data, even though this looks maybe not so big data-ish.
So what we have here now is what would actually have occurred in the universe, which is a network of cosmic strings. And to make this simulation would have taken around 15 terabytes of data. And again, what we have here is this is now a different type of radiation from the previous slide, but we can see what a network of strings would look like and what the radiation would look like over time.
Let's thank Amelia, soon to be in the future a Nobel Prize winner. We're going to bring out Hank Driscoll. I think a lot of people you know Hank. Hi, Hank.
Well, I stepped into Blue Sky a year and a half ago as the new CTO, but Blue Sky's been around 32 years. They've been making feature films since 1998, and right now we're in heavy crunch finishing up our latest film, Spies in Disguise, which comes out in Christmas.
You're an Embry user as well. CGI Studio
Spies
is
in
Embry
Disguise is using CG Studio, which is our proprietary render, and it absolutely heavily uses Embry. So Embry is pounding away frames right now on the queue 24/7.
And we're responding to any needs you have, things like that?
Absolutely.
The other cool thing you're doing is you are starting to look at these new technologies. You've recently been working with our Octane large-scale memory DIMMs. What's your experience there?
We started working with Rick and the team last October. We started poking at the new machine earlier this year. It's been a ton of fun. We're always looking for new opportunities to give ways for the artists to get more iterations in, for artists to be capable of doing more. The new machines are capable of putting a lot more RAM in the box, which is great, because that means we can put more stuff up on screen and we're not spending all our time culling and pulling things away to try and squeeze it into the boxes. The bigger boxes give us a lot of opportunity to do fun things. The persistent memory stuff's super exciting because we can do things with it we could never do before. So we're starting to have conversations about things like persistent state, where an artist is working on a scene and it took 45 minutes to load the darn thing, and they're in the middle of working, and then the application dies for whatever reason. how can we get it so the application comes back up and immediately because the scene stayed around in memory. That's a huge thing for our artists.
So fantastic. Can we, you heard my challenge about the 1000X. What do you think about that? Will you want to work with us on that?
No, super exciting.
Okay.
Everything that we can do to give the artist one more turn of the crank, everything we can do to enable the director's vision to get into the artist's mind and the artist to express that through the computer onto final frames, everything we can do to speed that up is a win.
Okay, well, we're looking forward to working with you and
absolutely.
Blue Sky
Yeah, we're
going
having a great
forward.
time working with Intel.
Thank you so much. Let me bring out Shane Ward, Principal Engineer from HP. He's going to tell us a little bit more about their experience with Big Memory and Octane. I understand, again, you're using Octane memory similar to Hank to help improve workloads and creativity.
Absolutely. So we've been working with persistent memory for a number of years now. And primarily we've been focused in on how can this new emerging and very disruptive technology help transform client computing. And by client computing, what I really mean are the applications that creators use every day. We basically ported over a number of applications, open source applications, to show the value of persistent memory. One of those is Blender. When you make changes, those changes are persistent, basically happen right in memory. So if you close your application without ever hitting save, without ever using autosave, basically you open back up the application and those changes are still there, which is really, really, really exciting. So HP is investing in partnering with other industry leaders who could take advantage of this new technology. For example, we're working with a geoscience company called CGG. We're porting over their geoscience application, visualization application over to persistent memory, and we are seeing some really exciting things.
That's awesome.
Yep.
Thanks for coming by.
All right, thank you.
Okay. Finally, the future is we are bringing Intel rendering framework to the Xe architecture GPUs in a way where we holistically use the GPUs and CPUs and our AI capability together. The notion of bringing all this stuff together has been talked about by Raja. It's called One API. And so in light of our movement and our plan to have a holistic environment that takes advantage of everything on the platform, we want to have a tagline, no transistor left behind. We want to take advantage of everything on the platform, sort of what Pixar was talking about. One API is going to break that paradigm, and what we want to happen is the software is waiting for the hardware, and we're going to switch the game there. And to talk about how that switch is going to impact Intel, I'm going to bring on Jim Keller, our Senior VP. Hey, Jim, how are you?
I want to talk about something a little different because I'm a transistor guy. Raj asked me to come talk to software developers and content creators about, what we're doing with computing, and I thought there's two really interesting things. One is the co-evolution of transistors, computer architecture, and software, especially in really high performance spaces, is really interesting. And it's evolved over time, right? And the other is, I came to work for Intel, which is the Moore's Law company, and the whole world is talking about how Moore's Law is dead. So here's a first funny graph, which is the number of lines of code generated by a line of code, essentially, is going up exponentially. Like, we generated all this performance, because there's a funny thing. Does everybody realize this? Like, people don't get smarter. We're not writing more code, but the code generators are generating an amazing amount of code. So this is a really beautiful picture. Bell's law is a really interesting thing because as the number of transistors increased, right, we actually went through different types of computer. Mainframe, mini, workstation, desktop, laptop, mobile, right? And as periodically the number of transistors got high enough, it basically created a new kind of computer. But in a real way, it was a smaller, faster version of that computer. And then when I joined Intel, I was talking to Raj about this, and he was projecting out something that's a little different, right? As we got more transistors, we went from single core to multi-core to GPU to AI. And these are really fundamentally different types of computing. The software paradigm that runs on them is changing, right? And the wave of innovation. And the really interesting thing, and one reason people keep predicting Moore's law is going to end, is because the existing paradigm, when you first establish it, there's a lot of room to grow, you exploit it, you make it better, and then there's a plateau, and when you're on the plateau, you think that it's fundamentally slowing down, right? Like, how do you make the next thing faster is complicated. I spent a little time working with Elon Musk at Tesla, and Elon had something he said I think is super important. First, figure out exactly what you want, and then figure out how to do it. Don't let the how define the what, right? There are so many technology adventures where you build an apparatus or a compiler or something to do the next step, and it has a limitation inherent in its own how. We build big processors, right? So here's a core, and then we put 28 of them on a die today, and there's going to be a lot more coming pretty soon. And we also can put multiple die in a package. There's 56 cores. And if we apply 50x scaling, just start thinking about 2,500 cores on a die. And we could put 4 packages on a board. We're going to hold a board with 10,000 cores in the near future. And 100 boards in 4 racks is 1 million processors, which is about, it's going to be about an exaflop. Right, so exaflop computing coming to a couple of racks near you in a not too distant future. As we develop those processors, so many things will change. The type of compute, the software stack, the memory bandwidth, the cache, and there's a co-evolution of the software stack, the hardware stack, and the transistors that go together. But the one thing that's, like if you're planning your future and you say, this is coming, then the software stacks you're going to build are going to radically change over the next 10 years, right? And I just want everybody to think, because there's 2 worlds. Moore's law is dead, where things aren't really going to change, or Moore's law is alive, and they actually are going to change radically, right? And I want you to think about the world where things are going to move really fast. And the fun part is to enable presentations like the next one. So Jules is going to come out and talk about gigapixels of beautiful high-resolution panels for everybody, right? And the computing behind that is on its way and coming very, very fast. So with that, I'll bring Jules on stage. Thank you very much.
Exascale computing is truly something that is going to revolutionize graphics, visualizations, our lives. So how many of you guys here are Star Trek fans? Everyone, as it should be. And what we're going to talk about tonight is our path towards something that Star Trek posited was many hundreds of years in the future, but is much closer to reality, the Star Trek holodeck. Now, for those that were around in 1987 and watched Encounter at Farpoint, the pilot episode, you may remember Riker walking into this room, the holodeck, and going inside of a completely virtual experience. And while Star Trek in this episode was hundreds of years in the future, the display technology to actually make holographic rooms possible is within reach. And to power that, we need exascale computing. It is not enough to rely on what we have today. Now, OTOY, my company, has been working on the problems, the hard problems really around the content creation pipeline, the things that we need to solve to make this work. And we've been doing that for many, many years. What's amazing is that here we are 10 years later, and the technology to make emissive holographic panels is actually happening with a company called Lightfill Lab, which we're partnered with. So 10 years from that point, we are now productizing many of the tools and techniques needed to make this work, including light stage capture, which is just won its 2nd Academy Award this year, Octane Render, the world's most popular GPU renderer, Orbex Media Player, which we partnered with Facebook and others to deliver this sort of volumetric content. We've been working on GPU rendering for 10 years, and we're now at the point, these really 2-year increments, we're now at the point where we're ready to render holographic content on holographic displays. And what that means is that you're rendering, as Jim was saying, about a gigapixel per square foot. And with that gigapixel, when you look at that holographic panel from any angle, you end up with what looks like something you see out of a window. It looks completely real. And to get to that point, you're talking about 60 to 100 teraflops per square foot. We need to look at things from a different way. We need ray tracing hardware. We need, of course, GPU cores. We need AI to clean up the noise like we're showing here and deliver about 100 to 1,000x the rendering performance so that we can get to multiple square feet of holographic display surfaces. In other words, enough to make the 6 walls of the Star Trek holodeck, which we're showing here, and ultimately to get to environments that you can actually move through. And that what we're showing here is about 40 megabytes worth of holographic data being loaded into a GPU and being rendered in about a millisecond. So if you're seeing a concert with a holographic display, you'll see actual things floating above you. It'll be absolutely amazing. It'll look real. It will not look projected. It will not look like it's CG. It'll look absolutely real. And as these displays are mass-produced, you're going to see holographic tables that will replace your iPad, your laptops. You'll be able to touch things. It'll be true Tony Stark-level technology. And if you have the money in the next 5 years, you will be able to build a holodeck. It'll probably cost you, many millions of dollars, maybe above 10 million, but it will be possible. These panels can be stitched together, curved around walls, floors, ceilings. And in order to even test this content, what we're showing at SIGGRAPH, and we did this last year, we're doing it again this year, is a prototype simulator that takes our holographic renders and tracks your head with shutter glasses so that we can see what a holographic display would look like without actually having to look at the prototype panels. The man, the myth, the legend, my good friend Rajan. Hey, how are you, sir? What we are announcing tonight is that Octane Render, the world's most popular GPU renderer, we are porting it to Vulkan, and it will run on Intel GPUs, including the Intel G.
There is a level of passion, persistence, and delusion, frankly, that is required to pursue things like what Jules is after. And Jules is certainly among less than a handful of such crazies I know in this industry. And I want to thank Jules for pushing the envelope for a long time. The first time I met Jules was 12 years ago. He was talking about petascale graphics, petaflops, that he needed petaflops in the GPU in 2007. And I was like, what? Right? We haven't even reached a teraflop at that point of time. If our CEO, Bob Swan, was here today, he would have shown you this picture. A picture of the journey we are in the middle of, from a PC-centric company to Intel powering the world. Very ambitious. We are in the middle of what will probably end up being the largest culture transformation in the corporate history. Now, Jim showed this slide that we are on a path to 100 billion devices as an industry. So if you look at Intel's strengths over the last 20 years, we've been great at a couple of different technologies. One is transistor, and the other is our CPU architecture. We need to expand our strengths beyond those two areas. So last year, we laid out our strategy and vision around our 6 pillars of innovation. And we are executing this strategy with energy and a sense of urgency that the company has never seen before. This sentence that I have, which I haven't still figured out how to fit in a tweet, is the one sentence Intel strategy. That Intel will deliver a diverse mix of scalar, vector, matrix, and spatial architectures, designed with state-of-the-art process technology, fed by disruptive memory hierarchies, integrated into systems with advanced packaging deployed at hyperscale with light-speed interconnect links unified by a single software abstraction with benchmark-defining security features. I wanted to share this picture with you. Jim talked about the 1 million core computer. I want to give credit where credit is due. Actually, this discussion started on a whiteboard with Tim Sweeney, who was trying to solve a problem with Fortnite on how to scale beyond a small number of users that are concurrently playing. And this is the crazy vision that we are after. And Jim Jeffers talked about our One API rendering toolkit and how we are going to leave no transistor left behind. In fact, not leaving things behind is a big theme at Intel. No partner left behind, no API left behind, no transistor left behind. We will talk a little bit about that. Now, this SIGGRAPH, for me, has always been about these two swim lanes. There is the offline swim lane, which you heard a lot about, and there are amazing amount of tools and content creation apps, predominantly running through the CPU, enabled by our Intel rendering framework. And one of the attributes of offline is it addresses, terabytes to petabytes of memory. And then the real time, which is amazing, the amount of energy and enthusiasm and demos that you see in real time, enabled by GPUs, with a lower memory footprint. Now, what is exascale vision? I'd say it is very, very simple from our standpoint. It is the convergence of both these worlds, where you can create and consume. You have game engines, the rich content creation tools, the rich apps, the VR and AR applications running on exascale graphics through One API and through exabytes of memory. Now, look at all of these things and say, okay, this is great, kind of bunch of graphics geeks and nerds talking about pixels and all of that stuff. But if you look at the financials, the content creation, offline content creation market is quite big. There are 50 million creators, 51.5 to be precise, generating about $34 billion of TAM between hardware and software. Now, most people don't talk about this because it sits next to this gigantic real-time market with gaming, with $205 billion TAM, with 2 billion users. But if you're paying attention to what's happening in the world, there are about 1 billion aspiring creators. The exascale creation and consumption opportunity ahead of us is greater than $250 billion. In about 10 years, this market will be over $1 trillion TAM, and over half the population of the world will be participating in this market. So that's the journey we are on. That's the ambition we are on. If our CEO was here, he would say this. We know we are pursuing a really hard problem, and this is his quote. If it were easy, anybody could do it. Because it's not, it's meant for Intel. And if it is not done with integrity, it's not worth doing. That's Bob Swan, CEO of Intel. Now, I want to close it with saying this is just the beginning. Just the beginning of what, you might say. It's just the beginning of an extraordinary party that's ahead of us. I'm looking forward to meeting you all again and enjoying the rest of the night. Thank you for being here, and thank you for the whole team making this happen.